Hello, rockhounds, and welcome back to Geology Dean's mini-series on igneous rocks. This is episode 6, and today we're tackling a cornerstone concept in geology, Bowen's reaction series. Ever wondered why different igneous rocks have such a specific mix of minerals? Well, a Canadian petrologist named Norman L. Bowen figured it out about 100 years ago, and his work is still fundamental today. Imagine a big pot of magma, a molten rock soup, slowly cooling deep within the earth. As it cools, not all minerals crystallize at the same time. Bowen's reaction series is like a roadmap that tells us the exact order in which these minerals form. It's a brilliant way to understand the evolution of magma and why we see such a diversity of igneous rocks. The series is split into two main pathways that happen simultaneously. On one side, we have the discontinuous branch. This side deals with the ferromagnesian minerals, the dark, iron and magnesium-rich ones. Think of it like a series of transformations. First, at very high temperatures, around 1400 degrees Celsius, olivine starts to crystallize. As the magma cools further, the early formed olivine crystals react with the remaining melt to form pyroxene. Cool it down more, and pyroxene transforms into amphibole. And finally, amphibole changes into biotite mica. Each step requires a reaction with the melt, which is why it's called discontinuous. It's a sequence of distinct mineral changes. At the same time, on the other side, we have the continuous branch. This pathway describes the evolution of just one mineral group, the plagioclase feldspars. Unlike the discontinuous side, this is a smooth, gradual change. At high temperatures, the plagioclase feldspar that forms is rich in calcium. As the magma cools, the crystals continuously react with the melt, incorporating more sodium and shedding calcium. So you get a gradual transition from calcium-rich plagioclase to sodium-rich plagioclase without any abrupt mineral changes. It's a continuous, seamless process. So what happens when both branches have run their course? Once the ferromagnesian minerals have finished their transformations down to biotite and the plagioclase has become sodium-rich, the remaining melt is now enriched in silica, potassium and aluminum. This leftover liquid crystallizes at the lowest temperatures to form potassium feldspar, muscovite, mica, and finally, quartz. Quartz is the last to crystallize because it forms at the coolest temperatures, around 650 to 700 degrees Celsius. This whole sequence perfectly explains why certain minerals are found together in rocks. For example, you'll find olivine and calcium-rich plagioclase in rocks like gabbro or basalt, which form from high-temperature magmas. And you'll find quartz, potassium feldspar, and sodium-rich plagioclase in granite, which forms from cooler, more evolved magmas.